So today we will be discussing about tool wear. So yesterday we discussed about cutting tool materials. Now the next topic is that is the tool wear. So what is a tool wear? Crater wear developed on the surface of at tool face at a small distance for the cutting edge. So crater, what is a crater wear if we talk of? Let's go first take off the nomenclature for the tool, that is this is the workpiece here, and this is the tool going in between this. So this is the chip going on in this direction here, and this was the initial shape of the tool, and this is the crater here. Basically the crater is going on above the tool here. So as the tool, this is flank of the tool, this is the shape of the tool after wear. Clear? So this is as the tool advances into this. This is basically the flank wear. This is the crater wear. Upon this, we'll be discussing all of the things one by one. Just see the figure clearly first. This is the face of the tool, and with the we can say the distance from the lower end to the upper end of this. This is taken as D, and this is the total length of crater wear. This is chip, and this is initial shape of tool basically. Initial shape of tool, and and after the cutting, it gives a change in the shape of the tool. This is known as the initial shape. This is the final shape, and the distance between the initial and final shape is taken as D. That is known as your crater wear. So it is developed on the rake surface. So this is the rake surface at a tool face at a small distance from the cutting edge. So this is run from a small distance from the cutting edge. This is the cutting edge. This is the small distance that is taken over this. Where it is caused by shear aberration between chip and tool face. So it is caused when there is shear aberration between the chip, and this is the chip going on this direction, and this is the face of the tool. So when there is this is caused due to the aberration between the chip and this of this part. Here, so diffusion of tool material at high temperature. Generally, what happens when we are cutting tool advances into the workpiece, it gets into because of the continuous cutting and the presence of friction, the tool gets heated up basically. Clear? So, what because in order to get it done, in order to get the metal, we can say taken off from the workpiece, it has to be beyond go beyond the temperature of that particular workpiece for this. And for this, these are basically the zones of high temperature zones are where the cutting edge is touching onto the tool. Where so the cutting edge where is touching onto the workpiece, it is taking off, and where the chip formation is taking place. So this all over this is basically is a high temperature area, high temperature zone in this case. And what happens basically at that high temperature, sometimes there is diffusion of tool material. The tool material diffuses with the workpiece in this case, and due to this, there is a wear in the crater of the at that part, that is known as the crater wear in this case. And next is the possible in ductile material due to continuous chip. So normally we have discussed earlier also when we are machining the workpieces in a ductile material, then there will be the you can say the production of continuous chips. And when these are continuous chips are going on, then what happens is they started diffusing with the tool, and that is the reason being on the high temperature zone, it takes off the craters onto the tool side, that is known as your crater here in this case. So increases the actual rake angle and make cutting easier in this case. So what it does, it increases the actual rake angle here, and the rake angle of this is this angle that is basically on this side as the rake angle is known as, and it makes the cutting easier for this, but weakens the tool wedges and increase the possibility of tool breakage. The overall problem with this is basically when it goes on advancing like this, the crater wear goes on, we can say advancing into the tool. After we can say a span of time, it will be taking off. It is weakening the tool edges. So all the edges of the tool will be weakened by this. And as far because we are working in a high temperature zone, what happens is when the tool edges are going to weaken with the we can say with the span of time, and as they goes on in the crater wear goes on increasing and increasing, and then ultimately a point will be reached when the it will be go the threshold value for the strength for the hardness of the tool, and what will be resulting in the breakage of tool. Clear? So what has happened, the major drawback for the weaken for crater wear is it weaken the tool edges. Clear? So slowly and steadily it goes on weakening up the tool edges and increase. Normally what happens is, as it goes on weakening, as there are chances of tool failure goes on increasing. So this was we were discussing about crater wear. Then comes your flag wear. So this is basically the part of the tool. Clear? So this is wear land, or VPP known as called as, this is face or this is flag. Face is the upper side of this, and flank is the sideways of the thing that advances into the tool. So what happens? It occurs on the tool flank below the cutting edge. So this is cutting edge, clear, and this is the tool flank normally, clear. So this is between the tool flank and below the cutting edge, underneath the cutting edge. So this part that is shown in the circle in this case. Friction or abrasion between newly machined surface of the workpiece and the tool flank results into flank wear. Clear? So what are the reasons for the flank wear is a friction or abrasion. Normally when the tool advances, this is the side, flank side that will be touching on to the, we can say with the workpiece in this case, other than the cutting edge. Cutting edge is at a point contact in this case, but the maximum contact is with the flank in this case. So there will be friction when it is being in contact with the workpiece and at the high temperature zone, and abrasion between the newly machined surface of the workpiece and the tool flank results in flank wear. So as the tool advances, the metal goes on taking off metal from this. Clear? So due to the friction and the abrasion of the newly, like the layer above layer, upper layer of the material goes on, workpiece takes off. Clear? And after that, when the above layer goes off, it coming on the new layer, that is the newly machined surface, comes into contact with this part. Clear? So the newly machined surface, when it is seen on that part of the surface of the workpiece, so it starts taking off the two flanks from this side. The flanks of this side that we have shown in the surface of this part, it takes off, starting off these sides from that part of this. Clear? So it increases cutting force and may cause tool failure. So what happens with this? As it goes on, the flank wear goes on this, increasing and increasing. So after some time, it goes the cutting forces, they get to increase manifold in this case, and with the increase in the manifold increase in the case of your tool forces, what will be it will be resulting in the failure of the tool in this part. Clear? So these are all the crater wear. There is a chances, and earlier we were studying upon this. It is making the tool edges, and the tool breakage is this case in this is the result of the crater wear. And in this case, in the case of your flank wear, it is the cutting forces that may increase manifold, and they may give chance to your increasing up of your flank wear for this part. So tool failure is basically going on. Your flank wear will slowly goes on increasing the cutting forces, and as the cutting forces will increasing, it will be resulting into the failure of the tool. Dimensional accuracy and surface finish of the machine part will be affected. So next impact of the flank wear will be as when we can the material will be taking off after this, the flank will be touching onto the surface of the newly machined part. So the newly machined part surface will there will be chances of that will be going up again over the machine surface for this part. So when it is going over the machine surface of this part, it will be giving some grooves, or we can say it will be taking off the surface of, it will be increasing the surface roughness of that newly machined part. It will be taking up on the that will be taking a scratches or the lines with there the flank is being contacted. Otherwise, the flank is rounded shape, but when the flank wear is taking on the area of the flank wear, when it will be touching onto the newly machined surface of this, it will be going on, will be taking on the scratches on the surface of the newly machined part, and the surface finish of the newly part will be affected by this, by the greatly affected by this. Secondly, the dimensional accuracy will be affected also by this, because when there will be it will be touching onto the machine surface, plus there will be not will be the smooth movement of the tool over the workpiece. So when there will be no smooth movement of the tool over the workpiece, it will not be taking off the required dimensions or required shapes that we are supposed to take off while the movement of tool over the workpiece. So this is, if we see, this is rear land, this is the tool, this is flank, and of this side normally it goes on, and it is, this is the cutting edge and this is below the cutting edge. Yes, so this is the rear land, normally we known as we call it as rear land, where the actual rear flank here is taking place. So below the cutting edge this is going on, and as it was going, it is going on to the flank rear land or face of the, near the face or below the cutting edge of the tool, there will be the registration of your flank rear in this case. So width of flank rear, that is VB, that is known as a rear land, we normally call it as. So it is basically a 0 point, that is increasing in this point 1, point 2, 0 0.3, 4, 5, 6, 7, 8, clear, and with the cutting time in this case. So this is initial breakdown, clear. So as with the cutting time and with the width, there is initial breakdown, and that is the lower width at the same flank here in this. And from again from point B to A to B, it is normally initial breakdown of the flank in this case. Then it goes on to the at a uniform rate with slowly with the cutting edge, with the cutting time in this case. So from B to C, normally nearby C, it goes at a uniform rate. Initial breakdown is at we can say a very lesser value of cutting time here, and that is up to the range of something like very low range in this part. Then from B to C, it is a uniform rate, almost uniform, not a uniform rate, because with the increase in time, there will be the increase in the flag wear of the tool. Here, and after C, when the cutting time exceeds some threshold value, almost in this case, like the threshold value is taken as something like 180 or 190 in this case. And after that, as the cutting time you can say precedes the value of 180 or 190 seconds for for this state, then there is a very much, we can say, increased rate of the we can say the plant wear in this case, and it will be resulting in the rapid breakdown of the tool also. Clear? So it is being done in number of stages. If we see, the first one is initial breakdown, where it starts in this case from A to B. If we see, it is initial breakdown, and it happens mostly in the starting of the cutting time. Yeah, so in the first few, we can say seconds, it goes for initial breakdown of the plant wear. Then from B to C, and that is a, we can say, a quite bigger range for this. Like from here, it would be approximately 10 or 20, from 20 to near about 180, here 170, 180 here of the cutting time. It is a uniform wear rate, and the graph is purely, we can say, a line that is being followed by this your width of flank and cutting time is properly followed in this case also. So it is therefore a uniform rate. As the cutting time is increasing, the width of flank wear is also increasing in this case. So as it goes on increasing and increasing up to a certain value, the threshold value for this at this point is, that is near about 180, 190 for this. As soon as it crosses 180 or 190, then hardly because most of the, if we see from this side, the most of the width in the plant wear has been done. Like from here, it is from, if we started from point B, it is from 0.1 to almost at the point C, it is 0.6. In between 0.55, if we say. So from starting from 10 to, we can say 0.55, it is taking the time of from 10 to like 180 here. So for the cutting time. So this is the at this rate, it is, although it is uniform, but still the width of land wear goes on gradually increasing in this case. As the cutting time advances, the tool also, or we can say the width of the flank wear also goes on increasing and increasing for that part of the wear. So, and after a certain value of threshold value of this, so after the point C, that is the value of this 180 near about cutting speed of 180. So it goes rapidly, a sudden, or we can say a very there is a rapid increase in the width of the flange wear after C2D. There is almost, if we see the curve is almost a straight line in this case. So what happens? It starts rapidly, the stresses go on increasing, and the width of the flange wear goes on increasing very cold after the value of 180 of the cutting time. So at this time, it goes suddenly, rapidly, it goes very much up, and at that time, there is chances of a rapid breakdown of the tool in this case. So this was, we can say, bifurcation between the width of flange wear and the distance between the cutting time. So it happens in three phases: initial breakdown, that is very short, or it starts almost in the starting a very short time. Then a uniform wear rate, that is in intermediate space, we can say, phase in this part. So it has a longer range, it has a longer value, and it has the width goes on gradually goes on increasing in this case. And after the point C, we see the third phase, that is the rapid breakdown. When it enters the rapid breakdown, it's just a matter of very short span of the time. So it goes on like rapidly, it goes on increasing, and there are chances of rapidly breakdowns. The tool breakdown occurs due to the plant wear of of a cut as compared with your cutting time in this case. So in this case, mechanism of tool wear, mechanical wear or abrasion is adhesion wear, diffusion wear, chemical wear, or electrolytic wear. Adhesion is basically the addition of the particles due to this. The tool wear there is addition with your workpiece material and the fusion over that part, that results in the wear of the part. Then third one is your diffusion wear. Diffusion is that is at high temperature zones, when there is a regions of high temperature zone, there is a rapid increase in the temperature of this, and that too rapid increase in temperature. Both the materials of the tool and the workpiece started diffusing with each other, and when they start diffusing with each other, there is the chances of they get diffused with each other, and that due to diffusion, that is erosion of the cutting tool also is taking place. Then chemical wear, due to the properties of the material in this case, and like the lubricants, chemicals that we normally use, that also occurs in, we can say, helps in the we can see chances of their chemical wear in this case. Then it comes your electrolytic wear. When using electrolyte in this case, like in case of electrolysis for this test. So when as it goes on like this, in the case of cathode and anode electrolysis, normally we see there is a wear on one electrode and wear on the other, that is done by the electrolytes, and that are because they are to place in between the electrolytes, and the purpose of electrolytes is to take off the wear easily, slowly, because they are also being as a chemical, they are chemicals, they are taking off the wear of the tool slowly and suddenly over the period of time in this case. So these were basically the one, two, three, four, five, we can say, mechanisms for this. These are mechanical wear. Normally, mechanical wear is all we see as it goes on replacing take off of the material. The material, some of the material will also be taken off from the workpiece also in that regard. So, and next part is your addition wear. Addition wear is the diffusion and diffusion of the tool. Chemical is that is the lubricant that we are using. They're reacting with the material of this tool on the workpiece, that is writing on this case. Then it is the chemical wear, the chemical, and then the last one is your electrolytic wear for that part.